Welcome to lesson 2.2. In this lesson, we're going to talk about the derivatives of polynomial functions. So we're specifically zoning in on those polynomials, and later we're going to expand to rational, radical, and then in future chapters like exponential and trigonometric, that kind of thing. So the first rule that we're going to talk about is the constant function rule. So I'm going to develop the rule for this. What you need to know is what shows up here in the box, but I'm going to show why it works, or like where it comes from up here. So we know that to find the derivative, we take the limit as h approaches 0 of the difference quotient. Now in this section here, our original function is f at x equals k, and k is just some constant number. So if I want to plug in the y values here, the y value for f at x is always going to be k. It doesn't matter what the x number is. And so if I change the x number to be x plus h, there's nothing for me to plug in or sub in here. So the y value is still just the constant k. So I'm going to plug in these two y values into the limit. They're both k. And then I can do the subtraction in the numerator. K minus k is just 0. So I get 0 divided by h, which is just 0. It doesn't matter what the h number is. Other than the h number can't actually be exactly equal to 0. But it's technically not here because h is approaching 0. And so I end up with the limit as h approaches 0 of just 0. And again, there's nowhere for me to plug h equals 0 in here. There's no direct substitution to do. It's just equal to 0. And we know that as a limit rule as well, right? When I'm taking the limit of a constant, it's equal to just that constant. And so what we find out here is that in summary, if f at x is just equal to some number k, then the derivative value will always be 0, no matter where I am on the, along the x-axis. Now, if I think about the graph of f at x equals k, well, that's just saying that along the graph, the y value is always equal to k. So every point along this function has a y value equal to k. And you can see here, it's just a horizontal line. And if I think about the derivative function tells me the slope of the tangent. Well, anywhere I draw the tangent along here, the tangent is also going to be a horizontal line. And so the slope of that is always 0. So that makes sense that comes out as 0. All right, the next thing we're going to talk about is the power rule. And again, don't forget, your responsibility is to know this stuff in the box here. The other stuff was just developing the rule, so you don't technically need to know that. The power rule, I'm not actually going to prove this absolutely. What I'm going to do is just look at the case where the power is equal to 3. So we're going to find the derivative for the function f at x equals x to the power of, we're going to use 3 here for the n value. And then we're just going to extend and say it's going to work no matter what the number is. If you want to see a full proof, there is a full proof in your textbook on page 77. So I'm going to take, again, I'm going to be using first principles. And again, we are choosing n equals 3, so that means that my function is now x to the power of 3. And I'm going to need x plus h in here. So f at x plus h, that's going to be x plus h cubed. And there is a trick for expanding this. You might remember it from past courses, but if you don't, you can just think about multiplying 2 of the brackets together first, and then you would get x squared plus 2hx plus h squared. And then you can multiply the third one in. So you'd have to multiply everything in the bracket by x, and then multiply everything in the bracket by h, and then you would collect your like terms. Oops. X. And so I see that there's a couple of terms here that are going to collect. I've got, for x squareds, I've got 2hx squareds and 1hx squared, that's 3hx squareds. And then for x's, I've got 1h squared x and 2h squared x, that's 3 of them. And so you might remember this pattern using Pascal's triangle, but if not, again, you can always go back and just multiply it out. Again, though, this development, you don't need to know this part here. We're coming up with a rule that we're going to put into the box down here. So I'm going to substitute in my expanded f at x plus h. You can see now why I didn't want to use like n equals 5 or something like that. And then I'm going to subtract f at x, which we said was just x cubed. And now I'm going to try to simplify this. So I've got x cubed minus x cubed, those simplify away. And again, in order to take the limit, I need to cancel out this h from the denominator. So I'm going to grab the common factor of h in the numerator. There's still some h's tagging along in there, but that's okay. What we really needed was this h to cancel. And now I'm taking the limit of this guy. I can do it. I can use some direct substitution. And I end up with 3x squared plus 0 plus 0. And so I get this 3x squared for my f prime at x. So notice here that I started with x cubed, and I ended up with 3x squared. And you might remember from our other lesson that when I had x squared, the derivative was 2x. And there's a shortcut for this. What's happened here is the exponent comes down and becomes a coefficient, and then I subtract 1 from whatever the exponent was. So, in general, if my exponent was n, I would bring that down and it would become a coefficient. And then the new exponent is just going to be 1 less than what I had before. So we're going to take a look at a couple of examples here. Oh, and also in Leibniz notation, I could also rewrite this rule and say that the derivative with respect to x of x to the power of n is equal to n times x to the power of n minus 1. And that would be in Leibniz notation. All right, so we're going to differentiate these different functions. The first one that we have here, the first one that we have here is just a constant. We've got h at x is equal to 7. So when I take the derivative, that's just a horizontal line. No matter where I draw the tangent, it's also going to be a horizontal line, and I get a slope of 0. So no real work to be shown there. You can just go right to 0. That's why we like these shortcuts, because now we're not going to write the limits. We're just using our little shortcut rule. For the next one here, we're going to take the derivative of k at x. And again, this one's our power rule, the second one that we just did there. I'm going to take this exponent 5, and it comes down as a coefficient, and then I just subtract 1 from the old exponent. And when we're talking about the power rule, we're always talking about an exponent on the variable that we're taking the derivative of. So it's not like, I wouldn't be like looking at f at x equals 2 cubed and taking the derivative using this rule. This is just a constant, so it would actually be using this rule over here. Right? There's no x here. It's got to be x to the power of something. All right, this next one is not technically a polynomial, but I can still use the power rule here. What I'm going to do first is actually rewrite this function so it looks like a power. So I want to have x to the power of something. So you might remember from grade 10, our negative exponent rule is what would bring a power down to the denominator. So this is actually the same as x to the negative 4. And we're going to use this trick all the time of using negative exponents instead of denominators whenever we can. So now when I take the derivative of this, I can use the notation dy dx, or I could use the notation y prime. Those are my two choices here. I don't have a function notation to use. Over here I can't use y prime because I'm given the function notation, so I will use that. And when I take the derivative of this, now it's just the power rule. So again, I take the exponent, bring it out front as a coefficient, And then I'm subtracting 1 from the old exponent on x. So it was -4, 1 less is -5. And then I can simplify this. If I'm going to simplify it, I don't want to have negative exponents in my answer. So I'll leave the -4 on top, but the x to the power of 5 comes down to the denominator. And now I'm done. All right, in part D, again, this isn't technically a polynomial function because the exponent here is a fraction. And what that means is that it's actually a root. So another way that I can think about this function is it's the square root of x to the power of 5. And you could put that power of 5 on the outside of the root if you wanted, or on the inside. So I'm thinking about that in the back of my head, but actually writing the exponent as a fraction is more useful to me. When I take the derivative here, again, I'm going to use the power rule. I'm going to bring the exponent out front and it becomes a multiplier or a coefficient. And then I'm just going to subtract 1 from the exponent. So I had 5 halves. If I subtract a whole, then I'll end up with 3 halves. Again, to simplify this, no fractional exponents when I'm simplifying. So I will rewrite this as 5 halves and then it's the square root of x cubed. Other versions of this, you could write 5 the square root of x cubed over 2. And again, the cubing can come to the outside here on either one of these, that's fine. So either one of those answers is fine. All right, on to our next rule, the constant multiple rule. Now we know from our last lesson 2.1 that if g at x is equal to x squared, then the derivative is 2x. We looked at that in our last lesson. So using first principles, I want to know what's the derivative if I put some k multiplier in front of that. So in this case, again, I'm not technically proving this because I'm going to use the generic function x squared, or not the generic, the specific function x squared instead of a generic g at x. So if I'm saying that f at x is k times g at x, then f at x here is going to be k times x squared. So that's what I'm using for this proof. All right, so I'm going to plug x plus h into my function. And then just subtract the original function. And what I want to know is, like, what happens to this multiplier k in front of this thing? I know that the derivative of x squared is just 2x, but like, where does the k factor into this? All right, so we'll expand the numerator and hopefully we can come up with a common factor of h that cancels out. When I expand that out, the two middle terms collect, right? When you expand it out, you're going to get x times h, and then you're going to get h times x, which gives you 2 hx's. And you can always take the time to write out that step, right? I've been practicing math for 20 years, so I'm used to that. I know what's going to happen, but if you're not there yet, then write it out. It's better to be right than to be fast. And now I'm going to multiply the k into the bracket. And what I get here is kx squared minus kx squared. So those guys cancel out. And now I'm left with an h that I can common factor out in the numerator. Those h's cancel away. Whenever you run out of space, just use an arrow to show where you're restarting. And now I can actually take the limit here because I've canceled away those h's. I'll plug in 0 for h. And I get 2kx plus 0, or just 2kx. And so what we notice here is when I take the derivative of this, the k is just hanging out. So another way for me to write this is I can put the k in front. And then remember, our g at x was x squared, and our g prime was 2x. So when I see this 2x here, it's the same as g prime at x. And so f prime at x is equal to just k in front of, as a multiplier, g prime of x. So when I have k times x squared, I just leave the k out front. It's just hanging around, and take the derivative of the function that comes after it. And then I can simplify afterwards. So again, if f at x equals k times g at x, then the derivative will be k times whatever the derivative of g at x is. Again, if you want to see a complete proof, that's on page 78, and it just won't use the x squared function. It'll keep a generic g at x in. All right, we're going to try to practice this. So in my first example here, I have a multiplier 5 in front of the function x to the power of 6. So to take the derivative of this, the 5 just hangs out, and then I take the derivative of x to the power 6. Remember, the power rule tells me bring the power out front, and then subtract 1 from the exponent. And then I can simplify this. I get 30x to the power of 5. Now, normally, once you start practicing, you're going to skip right to here. When you do this, you're just going to bring the 6 down and multiply it by the 5. You'll do it so automatically that you're actually later on in the course, you're going to forget that this was even a rule. But really, I am leaving the multiplier out front and then taking the derivative of the thing that comes after it. So I'm okay with you skipping there once you get that practice in and you're comfortable. All right, so the next one here, we've got g at x is equal to 8, and then x to the power of 3/2. I'm going to make a mistake here when I start this question, just because I want to show you something that I commonly see with students. So I'm going to leave the 8 out front, that's correct, and then taking the derivative of x to the 3/2, I bring the 3/2 out as a multiplier, and then I subtract 1 from the exponent. So this is technically correct. The problem here is the communication. You're still telling me that this is equal to g at x, and it's not. It's the derivative. So this is the mistake that people make. They forget to change the label to be the derivative. All right, now I'm going to simplify this. I'm going to do 8 divided by 2 first, because with multiplication and division I can switch that around. So I get 4 here. And so now I've got 4 times 3, that's 12. And then x to the 1/2, to simplify that again, I'm going to change that to a root. If you're not remembering your root rules, if you have x to the m over n, that's the same as the nth root of x to the power of m. And the m can go on the inside or the outside of the root. All right, the sum and the difference rule, I'm just going to give you this rule, and if you want to know why it works, you can check out page 79 in your textbook. The sum and the difference rule is that if I'm adding two separate functions or subtracting, so I've got p at x and q at x, and if I put a sum in between them, and if p at x and q at x are both differentiable, so I can take the derivative, then the derivative is nice and simple for us. I just take the derivative of p and take the derivative of q and add or subtract them, the same as what the original was. So if the original was adding, then I add the derivatives. If the original was subtracting, then I subtract the derivatives. This is really nice. It doesn't work out for other operations. So for adding and subtracting, you can do this, but not for multiplying and dividing. So we're going to do some separate lessons on those operations. All right, so we're going to use this idea of adding and subtracting here. In my first function, I don't have adding or subtracting. I actually have 3x minus 1 times another 3x minus 1, right? Another way for me to write this is like this. This is a multiplication, and I just told you the rule is more complicated. So what I'm going to do is actually just expand it out before I get started on the derivative. So 3x times 3x, and then I'm going to get 3x times negative 1, and then negative 1 times 3x. That gives you minus 3x minus 3x, or minus 6x, and then negative 1 times negative 1. Once I've expanded it all, then I can take the derivative, and the sum rule tells me I just take the derivative of each piece separately and add or subtract them together. So looking at the first piece, 9x squared, I bring the 2 down and multiply it with the 9. I get 18, and then I'm going to subtract 1 from the exponent. So you can write a 1 here if you want. You don't technically need to. And then I move on to the next piece. So I'm going to subtract the derivative of 6x. The derivative of 6x says take the exponent, remember the exponent was 1, bring it down and multiply it by 6, so that'll give me 6, and then subtract 1 from the exponent, so that'll now be a 0. And then taking the derivative of a constant, remember the derivative of the constant at the end here, 1, derivative is always 0. And then I can simplify this. So I've got 18x, and then x to the power of 0, remember that's always equal to 1, so I've just got negative 6 times 1. And I'm done. All right, the next one, again, I have an addition between two functions with x's, so I'm going to use this rule and just take a look at each piece separately. The first piece, I don't like how it's written because the x is in the denominator. So I'm going to bring it up to the top and give it that negative exponent. The second piece is just fine, so I'll leave it like that. This is still just g at x. I haven't actually taken the derivative yet. So now I'll take the derivative. Don't forget to communicate that, right? When are you switching to the derivative? And I'll take the derivative of each piece separately. So looking at the first expression, I'll bring the exponent down and multiply it with the coefficient. And then I'll subtract 1 from the original exponent. Same thing with the second piece here. I'm going to take the 3 exponent down, multiply it with the existing coefficient, and then I'll subtract 1 from the exponent. And now I'll just simplify this so that I don't have the negative exponent here. It's going to be negative 5 over x squared plus 6x squared. Now to simplify this, I can't have the fraction off to the side. So what I'm going to do is actually collect this into one fraction. I'm going to create a common denominator. So I want an x squared in the denominator. That means I also have to multiply the top by x squared. And what I'm going to get then is plus 6x to the power of 4 over x squared. And then we would rearrange this so that the largest exponent on x came first. And that's in simplest form there. So on the test, a lot of the big marks are on the first line for taking the exponent, and then we'll have some simplification that's going to come afterwards. All right, the next question, you're not going to have enough room on this page. If you've printed it off, you're going to have to grab a separate piece of paper or flip to the back to write this one. So when I read this question, the first thing that I notice is I want to write the equation of the tangent, and that tells me that I need the slope and a point in order to do that. The other thing that I'm noticing is that they are telling me I have to change the equation into standard form. So I'm going to keep my eye out for that. All right, so we want the equation of the tangent to this curve here at x equals 4. If I'm looking for the slope, that means that I want the derivative. Now, I'm going to use my shortcuts to take the derivative of this. I'm not going to use limits anymore, unless a question specifically asks me to. Now, before I use my derivative rules, I notice that there's a root in here. So I'm looking for like roots or x's in the denominator, and I'm going to change those to exponents. So instead of writing the square root of x, I'll write x to the 1/2. And so that's my original function. So now in order to come up with my equation, I'm going to find the slope. The slope of the tangent is the derivative. And so I'm going to take the derivative one piece at a time because it's adding and subtracting between the terms. So I'll bring the exponent 1/2 down and multiply it with 3. And then I'll subtract 1 from the exponent. Then for the second one here, again, I'll take the exponent down, multiply it with the existing coefficient. So it was a 1. I'm multiplying that by the 2. And then I subtract 1 from the exponent. And then the last piece here, it's taking the derivative of a constant. There's no x's, so it's just 0. So I can simplify this. I technically don't have to in this question because they are giving me an x value to work with. But I'm going to simplify just for practice. I have a negative exponent, which tells me that I need to move this x base down to the denominator. And then I also have a fractional exponent, which tells me to change it into a root. And then over here, 2 times x to the 0, that's 2 times 1, or just 2. So now that I have the derivative, I'm going to find the slope at x equals 4. I don't have function notation here, so I'm actually having to write out the words at x equals 4. If this was f prime at x, then here I would just write f prime at 4 is equal to. All right, so we've got our derivative. We'll calculate that. So I get 3 over 4. This is 2 times 2. So 3/4 plus 2. 2 is the same as 8/4, and so I get 11/4. All right, we've got our slope. Now, in order to come up with the equation, we also need a point. To come up with the point, all we're doing is subbing the x value into the original function. So again, I don't have function notation, so I'm going to write out at x equals 4. The y value is, and then I'm just going to plug it in. I'm going to use the original. And so we've got 3 times 2 here. And so we've got 7 overall. So we've got our point. Our point then is 4, 7. We've got our slope, so we can come up with our equation. The equation is going to look like y equals m x plus b. And then I'm going to sub in the point. So over here I've got 4 divided by 4, that cancels out and I'm left with 11, and then I'll just bring that over and subtract it. All right, so far for the equation we have that y is equal to 11/4 x minus 4. But this question asked us for standard form. So you might remember that standard form looks like this. And the rule here is that a has to be positive, and a, b, c have to be whole numbers, not fractions or decimals. So in order to clean this guy up and change it to standard form, I need to get rid of the denominator 4. So I'm going to multiply both sides of the equation by 4. And what that means is I'm multiplying each term by 4. And then I'm just going to rearrange this. I want the x term to be positive, so I'm going to leave it on the right-hand side, and I'm going to bring the y term over to join it. And there's my final answer. And we're all done lesson 2.2. Enjoy the homework.